In 1956, President Eisenhower signed a check for $25 billion to build the largest construction project in human history. 41,000 miles of interstate highway, cutting through mountains, spanning rivers, and connecting every major city in America. The machines that would do the fine grading on nearly every mile of that system were motor graders. And in 1956, most of them still ran on mechanical controls that had not fundamentally changed since the 1930s. The operators sat on open metal platforms, no enclosed cab, no rollover protection, no power steering. They wrestled banks of up to 15 mechanical levers while exposed to noise levels exceeding 105 decibels, choking dust clouds, and bone-jarring vibration that would destroy their spines over the course of a career. The dominant machine was the Caterpillar No. 12, and its mechanical control system had earned a savage nickname among the men who ran it. They called it the Knuckle Buster, not as a joke. The levers could snap back, jam fingers into gear mechanisms, and required increasing brute force as the machine aged. But here is the part that defies belief. Champion Road Machinery had introduced fully hydraulic grader controls back in 1928. Austin Western built the first all-hydraulic motor grader in 1937. The technology existed. It worked. And Caterpillar, the company that dominated the motor grader market, refused to adopt it for another 35 years. So why did the world's largest equipment manufacturer force its operators to use a mechanical control system from the 1930s while building the highways of the 1960s? And what did that decision cost the men who sat behind those levers? To understand the answer, we need to go inside the machines themselves. The 1950s were a golden age for motor grader competition. 7 major manufacturers were fighting for market share, each producing machines that reflected a transitional moment in construction technology. Diesel engines were replacing gasoline, and power was increasing rapidly, but hydraulic blade controls were still years away from becoming standard on most brands. Caterpillar dominated the market with 2 models that would define the decade. The No. 12, designated the 8T series, had been in production since 1947 and would become the most prolific motor grader of its generation. Inside Caterpillar's massive factory complex in Peoria, Illinois, workers assembled these machines around a D310 6-cylinder diesel producing 100 to 115 flywheel horsepower. The No. 12 shipped at 22,200 pounds with a standard 12-foot mold board. Over 17,000 units of the 8T series rolled off those assembly lines, a fleet of yellow motor graders that became the backbone of American road construction. Its smaller companion was the No. 112, the 3U series, running a 4-cylinder D315 diesel at 72 horsepower and roughly 19,300 pounds. Both machines shared a critical design feature that separated them from every competitor. They started via a 2-cylinder gasoline pony motor. On a frozen winter morning at a road construction site, the operator would crouch in front of the massive yellow grader, hand cranking the small pony engine through the radiator opening, then engage a starter pinion to the main diesel flywheel, release the compression, and wait for the big engine to catch and fire. On a January morning in Minnesota, with snow covering the dirt road in every direction, that process could take 15 minutes of frozen cranking before the diesel would turn over. But Caterpillar was not the only manufacturer building serious iron in the 1950s. Galion Iron Works, operating from their sprawling factory in Galion, Ohio, broke every size record in 1955 with the T700. At over 40,000 pounds and 190 horsepower, this enormous machine dwarfed everything else on the construction site. It was the largest motor grader the world had ever seen. Galion also introduced something that same year that no other grader manufacturer had attempted. The Gradomatic drive was the construction industry's first power shift transmission for graders. It used a torque converter and a 2-lever speed direction control system. eliminating the traditional clutch and shift sequence that required both hands off the blade controls during every gear change. Their smaller models, the 102, 103, and 104, served the mainstream market with International Harvester and Detroit diesel engines, ranging from 50 to 80 horsepower. Huber. Manufacturing of Marion, Ohio answered Galion's challenge with the 5D190 between 1955 and 1957. At 195 horsepower from a Cummins 6-cylinder diesel and 30,000 pounds operating weight, this heavy grader briefly claimed the title of the world's most powerful motor grader. But Huber also produced something entirely different. The Maintainer was a compact machine at just 35 to 40 horsepower that could serve as grader, loader, bulldozer, road sweeper, and sickle bar mower all in one platform. For small rural towns maintaining their unpaved county roads with a single machine and a single operator, the Huber Maintainer was the only piece of equipment they could afford. Then there was J.D. Adams of Indianapolis, Indiana. This is a name that every grader enthusiast should know, because J.D. Adams himself invented the leaning wheel grader concept back in 1885. That single innovation, tilting the front wheels to counteract side forces during blade work, remains fundamental to every motor grader built today, 140 years later. You can see it on every modern grader, on every highway construction site in the world. The company produced the models 220, 330, and 440 through the early 1950s, before being acquired by Letourneau Westinghouse between 1953 and 1955. Letourneau wanted Adams specifically for its grader expertise. Austin Western of Aurora, Illinois, was the technological radical. Their Pacer 99H offered all-wheel drive, all-wheel steering, and fully hydraulic blade control. The United States Forest Service tested the 99H in 1950 on mountain road construction in the San Bernardino National Forest in California, documenting its 75 horsepower diesel, 13-foot blade, and 28,000-pound operating weight. Austin Western had been building all hydraulic graders since 1937, more than a decade before any other manufacturer considered the technology viable. Champion Road Machinery of Goderish, Ontario, Canada, held the most remarkable distinction of all. Champion had introduced fully hydraulic grader controls in 1928. That is not a typo. 27 years before the Interstate Highway Act, this Canadian manufacturer was already selling hydraulic motor graders. By the 1950s, they offered the Model 507 Road Maintainer with full hydraulics and, incredibly, an enclosed operator cab. Those were radical features for a 40-horsepower budget machine. Champion exported heavily, shipping fleet orders of 60 or more graders at a time to the snowy highways of Alaska and to road construction projects across New Zealand. And Allis-Chalmers rounded out the field with the AD40, later redesignated the 45. At 23,000 pounds, with a Buda 6-cylinder diesel, producing 120 horsepower, this orange-painted grader sitting on a 1950s equipment dealer's lot carried a verified price tag of $13,740 a new in 1952. That is one of the few confirmed retail prices from the era, and adjusted for inflation, it translates to roughly $155,000 in today's money. The AD40's narrow T-frame design offered superior operator visibility compared to competitors, a genuine advantage when finish grading to tight tolerances. 7 manufacturers, 7 different approaches to the same fundamental problem. But only one of them, Caterpillar, had developed a mechanical control system so precise that it would hold off hydraulic technology for decades. To understand why, we need to look at how that system actually worked. A critical distinction for accuracy. Caterpillar motor graders used engine-driven mechanical gear systems, not wire cables. The term cable operated properly applies to the Letourneau-style winch and wire rope systems used on bulldozers and scrapers, where steel cables ran over sheaves to raise and lower blades. Some competing grader manufacturers did use true cable systems, but the dominant Caterpillar No. 12 ran on gears throughout. And the difference matters, because it explains both the precision and the punishment. The heart of the system was the power control unit, which operators and mechanics simply called a PCU. This heavy cast iron gearbox sat mounted at the operator's station, a maze of interlocking steel gears and shafts driven by a drive shaft connected to the engine flywheel through worm gears and a vertical shaft. That connection bypassed the flywheel clutch entirely, which meant blade controls operated whenever the engine was running, regardless of whether the transmission was engaged. The operator could adjust the blade while stationary, while moving, while shifting gears. The blade controls were always live. Inside the PCU, 2 gear trains distributed engine power through sliding jaw clutches to universal joints and telescoping shafts reaching every working component. Those jaw clutches had 4 teeth each, angled for easy engagement. Pull a lever, engage the clutch, power flows to that function. Release the lever, the clutch disengages, the anti-creep brake locks that component in position. Clutches did the work. The blade lifts used rack and pinion mechanisms. A drive shaft-driven pinion extended a rack mounted on the lift cylinder rod. No hydraulic cylinders anywhere in the system. A long radius curved rack enabled the side shift function, giving the No. 12 its legendary blade range. The blade could be positioned for 90-degree bank cuts, with 7 feet 4 inches of reach outside the wheel line. For a machine weighing only 22,000 pounds, that was an extraordinary working envelope. The anti-creep brakes were the engineering reason Caterpillar could resist hydraulics on technical grounds. These were 2-piece clutch yokes, with coil springs pressing against the clutch hub. When the operator released a control lever, those springs clamped down and held the blade in exactly that position. No movement, no drift, no slow settling under load. Early hydraulic cylinders leaked past seals under sustained load, and the blade would slowly creep downward. On a motor grader cutting drainage slopes to 1/4 of an inch per foot, even tiny blade drift destroyed the grade. Caterpillar's mechanical brakes eliminated that problem entirely. A shear pin in the vertical drive shaft provided overload protection. If the blade struck a buried boulder or an unseen obstruction, the shear pin would snap before the gear train could be damaged. Operators carried spare shear pins and could replace them from the seat without climbing down. It was crude. It was reliable. And it worked in conditions that would have destroyed the hydraulic hoses and fittings of the era. The No. 12 also offered a 2-speed control shift, fast gear for coarse blade movements, repositioning the mold board between cuts or swinging the blade to a new angle, and slow gear for finish work, where experienced operators could hold accuracy to 1/8 of an inch. That is the thickness of 2 stacked credit cards, achieved through pure mechanical precision with no electronics, no sensors, and no GPS guidance of any kind. But extracting that precision demanded something extraordinary from the operator. The controls of a 1950s Caterpillar motor grader were a wall of steel levers surrounding the operator's seat. Left blade lift, right blade lift, circle rotation to angle the blade, circle side shift to move it laterally, blade tip forward and back, wheel lean left and right, scarifier raise and lower, gear speed selection, plus the large steering wheel, which was manual without power assist unless the buyer paid for the extra cost option, plus the clutch pedal, plus the throttle, plus the transmission shift lever. The operator sat surrounded by steel controls on all sides. By the time Caterpillar introduced its M-Series joystick controls in 2007, the company documented that the new system replaced up to 15 individual levers and a steering wheel with 2 joysticks, a 78% reduction in operator hand motions. That number reveals just how many individual movements the 1950s operator was making on every single pass. And those movements were not gentle. The dog clutches that transmitted power wore progressively stiffer with use, particularly on the blade lift controls that saw continuous operation throughout every shift. The Caterpillar 14B, introduced in 1959, was specifically noted by operators for controls that were, in their words, quite stiff and almost painful on the wrist. The progressive degradation of these clutches over thousands of hours of operation is exactly why operators called the system the Knuckle Buster. The levers could snap back without warning when a clutch tooth failed to engage cleanly. They could jam fingers into gear mechanisms during rapid adjustments. And they required increasing brute force as the machine accumulated hours, meaning the oldest, most worn machines punished their operators the hardest. Experienced grader operators developed a physical intuition that bordered on a sixth sense. They could feel grade changes through the seat of pants. They could sense when the blade bit too deep by the change in engine tone. They could hold a crown on a gravel road by watching how material rolled off the moldboard while simultaneously managing 6 or 7 lever positions, the steering wheel, and the throttle. Motor graders were, and still are, widely regarded as the single most difficult of all earth-moving machines to operate. Developing the eye and seat of pants feel for finish grading took years, not weeks, not months, years. And the men who developed that skill did it while sitting on open metal platforms with absolutely no protection from anything. The operator's station on a 1950s motor grader was positioned midway between the heavy steel blade and the rear tires, high above the unpaved road surface. This placement had been standard since the 1931 Auto Patrol design because it gave the operator the best possible view of the blade edge and the ground it was cutting. But it also meant the operator sat in the most exposed position on the entire machine. There was no enclosed cab, no windshield on most configurations, no air conditioning, no heater, although heater boxes were available as optional accessories at extra cost, no air ride seat. The operator sat on a basic metal seat, sometimes fitted with a thin cushion, bolted directly to the rigid frame of the grader. Every bump, every rut, every rock the tires hit transmitted directly through that frame, through that seat, and into the operator's spine. The noise was devastating. Caterpillar and Case have documented sound levels of 105 to 109 decibels outside their motor graders before modern noise reduction engineering. On a 1950s open cab grader with a D318 diesel running at full throttle, just feet behind the operator's head, those levels hit directly for entire shifts. There was no hearing protection. Earplugs existed but were rarely worn. Modern enclosed cabs reduce operator noise to approximately 72 decibels. The decibel scale is logarithmic, meaning the 1950s operator experienced roughly 1,000 times the sound intensity of a modern operator. The 8-hour OSHA permissible exposure limit of 90 decibels did not exist until 1970. Whole-body vibration was equally destructive, just slower. The rigid frame transmitted every terrain irregularity directly to the operator. NIOSH research confirms that whole-body vibration creates a 4.06 times greater risk of lower back pain in equipment operators. Studies documented strong correlations with lumbar disc degeneration and herniation. These injuries build over years, not single incidents. A young operator in 1952 would not feel the damage until the 1970s, by which time the connection to decades of vibration was nearly impossible to prove. Dust exposure was constant and completely unmitigated. Motor graders exist to move earth. The blade cuts, spreads, and shapes soil, generating enormous dust clouds that the open platform operator breathed directly throughout every shift. Added to the airborne soil was diesel exhaust from the engine positioned directly behind the operator's head. Crystalline silica in the soil causes silicosis when inhaled over years. Diesel exhaust particulates are classified as a Group 1 carcinogen. A grader operator in 1955 inhaled both simultaneously, shift after shift, year after year, with no respiratory protection and no medical monitoring. By the time symptoms appeared, often decades later, the damage was irreversible. Modern motor graders feature pressurized cabs with HVAC filtration systems specifically engineered to seal out dust and fumes. Weather exposure ranged from brutal to lethal. The Alaska Road Commission maintained 3,700 miles of highway by 1955, using a fleet that included 139 road graders. Those operators worked through Alaskan winters at 40 degrees below zero on open platform machines. Army engineer William Griggs recalled that the equipment was not designed for sub-zero weather, and trucks had to run 24 hours a day to prevent freezing. Reports documented that many men died of exposure. But the most dangerous absence of all was rollover protection. Throughout the entire 1950s, no country on Earth mandated rollover protective structures for motor graders. Sweden enacted the first such legislation in 1959, and only for agricultural tractors. The Society of Automotive Engineers standard for motor grader rollover protective structures was not published until 1971. OSHA mandated rollover protective structures for graders manufactured after September 1, 1972. Motor graders are particularly vulnerable to rollovers because of their high center of gravity and the nature of their work. They operate on slopes, on unfinished road shoulders, on soft ground, and at the edges of excavations. The blade, when fully extended to one side for a bank cut, shifts the center of gravity dramatically. On a 1950s grader with no rollover protective structures, a rollover was almost certainly fatal. The operator had nothing to hold on to and no structure to create a survival space. Research confirms that rollovers were the leading cause of death among heavy equipment operators during the study period from 1992 to 2002, well after rollover protective structures mandates. In agriculture alone, tractor rollovers killed 1,412 operators between 1992 and 2005. No grader-specific fatality data from the 1950s exists because the Bureau of Labor Statistics did not begin systematic tracking until 1992. The overall workplace fatality rate in the early 1950s was approximately 21 to 24 deaths per 100,000 workers, roughly 5 to 6 times the modern rate. The men who operated these machines understood the risks. They accepted them because the alternative was no job at all. And in 1956, there was suddenly more work for motor grader operators than at any point in American history. If you have been watching this far, and you appreciate deep documentary content about the machines that built the modern world, hit like and subscribe. We cover construction history, equipment engineering, and industrial disasters every week. Now let us talk about the biggest construction project ever attempted. On June 29, 1956, inside the White House in Washington, D.C., President Dwight Eisenhower signed the Federal Aid Highway Act into law, authorizing $25 billion for 41,000 miles of interstate highways. Adjusted for inflation, that initial authorization alone equals approximately $220 billion in today's money. The total cost over 35 years of construction would reach $425 billion, and the project would displace over 475,000 households. The first construction contract was awarded for Interstate 70 in St. Charles County, Missouri, with groundbreaking on August 13, 1956. By December 1962, just 6 years in, 14,300 miles were open to traffic. and over $15 billion had been spent. The pace was staggering. Motor graders were essential at virtually every phase of interstate construction. Subgrade preparation, fine grading for drainage specifications, shoulder shaping, ditch cutting, base material spreading, and slope cutting all fell to the grader operator. On a major interstate project, graders might run 12 to 16 hours a day, with operators trading shifts to keep the machines working. The specifications were unforgiving. Federal standards required pavement surfaces smooth within 1/8 of an inch over a 10-foot straightedge. Cross slopes for drainage had to fall within 1/4 of an inch per foot. On a subgrade stretching 6 lanes wide plus shoulders, maintaining those tolerances with mechanical lever controls and no electronic guidance required an operator whose hands, eyes, and instincts functioned as a single integrated system. One lever pulled a fraction too far, and the grader could cut a low spot that would hold standing water for years. The timing created an extraordinary contradiction. When interstate construction peaked in the late 1950s and early 1960s, the dominant graders on the job were still running mechanical controls. The Caterpillar No. 12E, the Adams 440, and the Galion T500 and T600 were the machines building America's modern highway network. Caterpillar's first hydraulic-assisted grader, the 12F, did not arrive until 1965. Full hydraulics on a Cat grader did not come until the 12G in 1973. The largest public works project in American history was built substantially by operators running knuckle-buster machines on open platforms without rollover protection. The military dimension adds another layer. Korean War engineer construction battalions, including the 43rd, 62nd, 84th, and 453rd, built muddy supply roads through the steep Korean mountains using motor graders under combat conditions. Heavy monsoon rains turned roads into impassable quagmires. Bitter Korean winters froze equipment and soldiers alike. Training was minimal. One account noted that many operators had no experience on anything bigger than a pickup truck and learned how to run graders on the job in a war zone. That informal training pattern was not unique to the military. The International Union of Operating Engineers, founded in 1896, represented grader operators on civilian projects. But formal apprenticeship programs were not universal. Training was overwhelmingly hands-on, passed from father to son, from experienced operator to new hire. One operator recalled that when he was old enough to talk and take care of himself, he rode the grader every other day with his grandfather. Another described his first solo day on a vintage Caterpillar No. 12. He did not even know how to start the pony motor. On his first day, he put the grader in first gear, let out the clutch, lowered the blade until it made contact, and figured it out from there. This informal apprenticeship system produced operators of extraordinary skill. The best could read soil conditions by the color and texture of material curling off the moldboard. They diagnosed mechanical problems by sound alone, catching failing components before they broke, and stranded the machine miles from the nearest shop. But the system also produced operators who were undertrained, working machines they did not fully understand. A new operator might be handed the keys to a 22,000-pound grader after watching someone else run it for a few days. No written test, no licensing requirement, no minimum training hours. The result was predictable. Accidents, injuries, and fatalities were accepted as the cost of building roads. But throughout all of this, a question persisted. Why did Caterpillar, the dominant equipment manufacturer on Earth, resist hydraulic controls for so long when competitors had proven the technology decades earlier? The answer is not stubbornness. It is engineering. As equipment historians have documented, Caterpillar's reasoning was their distrust of hydraulics' ability to hold position without leaking down. And that distrust was not irrational. Early hydraulic systems were expensive to maintain, slow-acting, and prone to fluid leaking past cylinder seals. On a bulldozer, slow hydraulic creep meant the blade might settle a quarter inch over a pass. Annoying, but manageable. On a motor grader cutting drainage slopes to 1/4 inch per foot, that same creep would destroy the finished grade. Creep was the enemy. Caterpillar's mechanical anti-creep brakes solved this problem completely. Those spring-loaded yokes pressing against the clutch hubs held blade position with absolute reliability. No temperature sensitivity, no seal degradation, no hose failures. The system worked identically whether the machine had 100 hours or 10,000 hours on it, provided the springs and clutch surfaces were maintained. Wire rope systems had their own creep problems as cables stretched. Hydraulic systems leaked. Caterpillar's gear drives held. Period. The transition at Caterpillar was deliberate and gradual. The number 12E, produced from approximately 1959 into the 1960s, was the last model with fully mechanical gear drives throughout. It remained the pure knuckle buster, the machine that old-school operators swore by and young operators cursed. In 1965, Caterpillar introduced the number 12F with what the company called power-assisted planetary controls. This was a hybrid system. Hydraulic assist helped the operator engage the mechanical gear trains, reducing the physical force required, but the underlying power transmission remained mechanical. The 12F also introduced standard power steering for the first time on a Caterpillar grader, eliminating the arm-wrenching effort of turning the heavy front wheels through manual steering on previous models. For operators who had spent years wrestling the steering wheel on a 12E while simultaneously managing blade levers, power steering alone was transformative. The full brake came with the number 12G in 1973. This model brought fully hydraulic blade controls, Caterpillar's first articulated grader frame, and a CAT 3306 engine producing 135 horsepower. The articulated frame was arguably as significant as the hydraulic controls because it allowed the grader to work at an angle to its direction of travel without crab-walking the entire machine. For ditch cutting and tight radius work, articulation transformed what a grader could do. Operator response to the transition was divided. Veterans expressed real preference for the old ways. The consensus was that if you were going to buy a Caterpillar, get the mechanical version, and if you were going to buy an International Harvester, get hydraulic. Gear advocates cited bulletproof reliability, no hoses to snag on brush or rocks, and the ability to lower the blade under its own weight indefinitely. But even the strongest advocates of the old systems acknowledged reality. As one operator put it, he liked modern hydraulic dozers much better, but he was glad he had a chance at old-school cable and mechanical machines. Another captured the transition's fundamental problem. The mechanical systems got expensive to maintain, and the operators that knew how to run them retired. Once the generation of operators who had learned the knucklebuster system aged out of the workforce, there was no one left who could efficiently run the old machines. The knowledge was embodied. It lived in the hands and wrists and the seat of the pants. And when those operators retired, it went with them. The gulf between what an operator in the 1950s experienced and what a modern grader operator works with is almost incomprehensible in scope. In the 1950s, the Caterpillar number 12 produced 100 to 115 horsepower. Today, the modern Caterpillar 140 GC, rolling off the assembly line in bright yellow paint with a fully enclosed glass cab, produces 196 horsepower, nearly double the power while being vastly more fuel efficient. The vintage number 12 weighed roughly 22,200 pounds. The modern 140 GC operates at 38,900 to 42,100 pounds, nearly double the mass for greater stability, blade-down pressure, and traction. The 1950s operator managed 8 to 15 mechanical steel levers for blade control alone. The modern operator sits in an air-conditioned cab, using either a simplified lever bank or 2 joysticks with fingertip controls. The 1950s operator wrestled a manual steering wheel, turning the front axle through pure arm strength. Modern graders use full hydraulic steering with an articulated frame, allowing the operator to steer with fingertip pressure. The open platform of the 1950s has been replaced by a pressurized ROPS and FOPS cab with air conditioning, heating, an air ride seat, and noise reduced from over 105 decibels to approximately 72. That is a reduction in sound intensity of roughly 1,000 times. The hand crank pony motor start has been replaced by push-button electric start. Perhaps the most transformative change is invisible. The 1950s operator read grade from wooden survey stakes planted every 50 feet along the road, checking blade position by eye and feel. The operator would lower the blade, make a pass, stop to check against the stakes, adjust, and repeat. Finish grading a quarter mile of road might take an entire shift of repeated passes. Today, GPS-based machine control systems hold blade accuracy to 1/4 inch automatically. The system adjusts faster than a human hand can react. GPS grade control improves productivity by 30 to 50%, while reducing survey costs by up to 90%. Caterpillar's cross slope. Assist alone reduces wasted material by up to 40%. A modern operator can finish grade in a single pass, what took the 1950s operator half a day. A verified 1952 price for the Allis-Chalmers AD40 was $13,740. Adjusted for inflation, that translates to roughly $155,000 in 2025 money. A modern Caterpillar 140 GC sells for approximately $197,000 to $415,000, depending on configuration. In real terms, motor graders have roughly doubled in inflation-adjusted cost while delivering transformatively greater capability and keeping their operators alive. The 1950s motor grader story is not simply one of primitive machines and suffering operators. It is a story of remarkable engineering within the constraints of its time. Caterpillar's mechanical power control unit achieved 1/8 inch blade accuracy through pure gear-driven precision. That engineering achievement held its own against hydraulic technology for 35 years on legitimate technical merits. The system was rugged, field repairable, and reliable in conditions that would have destroyed the hoses and seals of 1950s hydraulic components. The operators who mastered these machines possessed a craft skill that has no modern equivalent. GPS grade control and joystick operation have made motor graders dramatically more productive and incomparably safer, but they have also made the tactile artistry of the cable and gear era effectively extinct. The human cost of the mechanical era was real and largely unrecorded. No comprehensive fatality data exists for 1950s grader operators because systematic tracking did not begin until 1992. The roughly 5-fold reduction in American workplace fatality rates since the 1950s reflects the cumulative impact of OSHA, rollover protection mandates, enclosed cabs, hydraulic controls, and air ride seats. Each innovation addressed a specific dimension of the punishment that motor graders of the 1950s inflicted on the men who ran them. What remains most striking is the overlap between the interstate highway construction boom and the mechanical grader era. The largest public works project in American history, those thousands of miles of concrete and asphalt stretching across the American landscape, was built substantially by operators running knuckle busters on open platforms, without rollover protection, without hearing protection, without filtered air, in temperatures ranging from desert heat to Arctic cold. That fact deserves its place in the documentary record alongside the engineering achievements of the highways themselves. The roads we drive today were graded by hand, lever by lever, pass by pass, by men whose names were never recorded and whose injuries were never counted. And their machines, the knucklebusters of the 1950s, were among the most demanding pieces of equipment ever built. If this story was worth your time, the video on screen right now covers the decade that came before. Those are the 1930s motor graders, when the machines were even more primitive and the operators even more exposed. Click it now.